Hi, in this video, we are going to look at roots of polynomials or zeros of polynomials and continue the journey into the section on polynomials. So we start off by specifying some notation that we'll be using for this video. So this notation that we use here is D is used to denote the set, used to denote the set Z union Q union R union C. Because don't want to keep saying in set of integers or rational numbers or real numbers or complex numbers. So we are going to say d of x basically means the set of all polynomials where the coefficients could be in set D, and basically D is this set. A set of integers or rationals or reals or complex numbers. So let's start by understanding how we figure out the roots of a polynomial. So let fx be this polynomial an x bar n plus a1x plus a naught belongs to the set d of x. What is the root of this polynomial? If a number alpha is such that f of alpha is equal to 0, f of alpha is 0, then alpha is a root or a 0 of f of x. That is the basic definition of a root. Now, we have a lot of standard results that you might be familiar with. The first one is the factor theorem. Factor theorem, which says that if alpha is a root of f of x, then x minus alpha is a factor of f of x. Factor of f of x. This is pretty standard stuff. So from the factor theorem, we can deduce that if you have alpha 1, alpha 2, and alpha k belonging to D are distinct zeros, of f of x. Distinct zeros means all of them are different from each other and no root is being basically repeated. Then f of x is divisible by x minus alpha 1, x minus alpha 2, this product till x minus alpha k. Because all of these individual terms are all factors of f of x, right? The third point is an nth degree polynomial. An nth degree polynomial in D of x has at most n distinct zeros. This is obvious because each zero makes a linear factor for the polynomial. So if the overall polynomial has degree n, there must be at most n zeros. Then we can say this is a very important result. If a polynomial f of x which has nth degree, so it is an x bar n and so on till a1x plus a naught in D of x, has greater than equal to n plus 1 zeros. So we have a polynomial with n degree, but it has more than or equal to n plus 1 zeros. Then we say that f of x is identically 0. F of x is identically 0 because it it has more roots than possible, so it must be an identity. So it is identically 0 or f of x is equal to 0, the 0 polynomial. This property will be used many times in problems, so understand this. Basically, the meaning is that a quadratic equation is given, and if you have three or more than three roots of the quadratic, then the quadratic is identically 0, which means all its coefficients must be 0. So similarly for any n degree polynomial as well. The next idea is a consequence of the previous one, which is known as the identity theorem. The identity theorem. So it says, let f of x and g of x belong to the set d of x if there is an infinite number of alpha belonging to d, infinite number of alpha belonging to d, such that f of alpha is equal to g of alpha, f of alpha is equal to g of alpha, then the two polynomials are identical. Then the two polynomials fx and gx are identical, or we can say fx is equal to g of x. Basically, if you have infinite alpha such that the values of the polynomial are equal, and even if the number of alpha here is not infinite, it is more than the degree of the highest polynomial, more than both their degrees, then also we can say that the two polynomials are identical. Basically, the way to prove it would be to take a new polynomial h of x, which is f of x minus g of x, and say that since they have infinite roots for h of x, then h of x must be identically 0. And if h of x is identically 0, f of x is equal to g of x. So that is the way to do that. Now, the next point is this one. Let f of x belong to d of x, and alpha is a 0, and alpha is a 0 of f of x. If f of x is divisible by x minus alpha whole power m, but not by x minus alpha whole power m plus 1, that is, f of x has x minus alpha power m as a factor, but not m plus 1. So that means alpha is a root which has a multiplicity of m. It's a repeated root, it has multiplicity m. So f of x can be written in this case as x minus alpha power m times g of x, or we can write that as q of x, thinking of it as a division, where q of x also belongs to d of x, and q of x is not equal to 0. In that case, we say alpha is a repeated root of f, repeated root of f of x, and has multiplicity m, multiplicity m. So it is repeated m times. Okay. Now, the next thing that we'll talk about is congruence equation modulo a prime. Congruence equation modulo a prime. Basically, we are going to take a polynomial f of x modulo a prime. So let f of x be a polynomial, with integer coefficients, with integer coefficients, and p be a prime number, and p be a prime number. Now, if an integer a satisfies this relation, satisfies f of a is congruent to 0 mod p, then a is a 0 of f of x mod modulo p, right? So basically, you can say that integer a, when you put the integer in the polynomial, you get the value f of a. And if the value of f of a is congruent to 0 mod p, we say that a is a 0 of f of x modulo p, right? Just adding on to that idea, if a is congruent to b mod p, you can always realize that in that case f of a will be congruent to f of b mod p. If a and b are congruent to each other modulo p, you will get that f of a and f of b will also be congruent to each other modulo p. So that is something that sometimes becomes useful. The next idea is Lagrange's theorem. So let's see what this says. Okay, so here if p is a prime number, if p is a prime number and f of x is a polynomial with integer coefficients, and f of x is a integer polynomial such that its degree modulo p is n. Degree modulo p is n. We saw in the previous video what the meaning of this statement is, that the polynomial's degree modulo p is n. What this means is the highest power of the coefficient which is not divisible by p is n. So we saw some examples in the previous video where we took multiple polynomials modulo different prime numbers. If all the coefficients of the polynomial are divisible by p, then the degree is undefined. But whichever term has a coefficient which is not divisible by p, the highest degree term like that gives us the degree of the polynomial modulo p. So in this case, we are saying p is a prime number and fx is an integer polynomial such that its degree modulo p is n. Then the equation fx is congruent to 0 mod p. This equation has at most n distinct solutions. And what do we mean by distinct solutions? Solutions that are not congruent to each other. Solutions that are not congruent to each other modulo p. So Lagrange's theorem is a way of saying that the similar statement that if your degree of a polynomial is n, the number of roots are n. So now we are saying it with reference to polynomials modulo p, right? So if fx is an integer polynomial such that its degree of modulo p is n, then this congruence fx is 0 mod p, this equation has at most n distinct solutions which are incongruent to each other modulo p, right? That is the statement of the theorem. Now, the next thing is let f of x be equal to an x bar n plus an minus 1 x bar n minus 1 and so on till a1x plus a naught. And this is an integer polynomial, belongs to this set z of x. Here, let's say p is a prime and n is less than p, right? If f of x is congruent to 0 mod P has at least n plus 1 solutions, n plus 1 solutions that are not congruent, that are not congruent to each other, modulo P, then fx modulo P is a zero polynomial, is a zero polynomial, that is, all its coefficients are divisible by P. All its coefficients must be divisible by P. So this is a consequence of Lagrange's theorem. So initially, in the previous point, we said that Lagrange's theorem guarantees that fx congruent to 0 mod P has at most n solutions if the degree of the polynomial modulo P was n, right? Here we are saying if the same congruence has more than n solutions and the degree of the polynomial is n, in that case, the fx modulo P is basically identically zero, or all its coefficients are all divisible by P, right? So this is like the theorem that we saw earlier for regular polynomials, but now we are applying it to integer polynomials modulo a prime. Okay. The next idea is the rational roots theorem. This is quite a famous theorem, so you might be aware of this. I will just state it here. Let f of x be written as an x bar n and so on till a1x plus a naught, and this is an integer polynomial. This is an integer polynomial where n is greater than equal to 1 and an times a naught is not equal to 0, right? We also have a condition here that the GCD of all of the terms an2, a1 and a naught, the GCD of all of these terms is 1. So the set of coefficients have GCD 1. In that case, if B by C, where B and C are coprime, is a rational root, of f of x, then C must divide an and B must divide a naught. This is the main part of the theorem. So what is the setup of the theorem? F of x must be an integer polynomial. The first and last terms should not be 0. And each of the coefficients, if you take the GCD of all the coefficients, the GCD is 1. So they are sort of co-prime to each other. In that case, if B by C is a rational root where B and C have been reduced to lowest terms, so B and C numbers are co-prime to each other, then C, the denominator, must divide the first coefficient, an, or highest degree coefficient, and B, the numerator, must divide the constant term. So that is the statement of the theorem. Now, we know since there is only a finite number of divisors, only a finite number of divisors of, say, a non-zero integer like a0 or an. So all rational roots of such integer polynomials, can be found, because You can just list down all the possible divisors of a0 and an and try to form possible rational roots. And then you can check with the equation itself whether they are actual roots or not, right? So rational roots theorem gives us a way to find all the rational roots for a situation where a integer polynomial satisfies these conditions. Remember, these are the conditions that it must satisfy in order for the theorem to be applicable, right? Okay, let's move on to the next idea. The next idea is basically the fundamental theorem of algebra, which was stated by Gauss. And this theorem says that any non-zero polynomial, any non-zero polynomial in C of x, with complex coefficients has at least one complex root. It is from here that everything flows, because if it has at least one complex root, you can factorize x minus alpha, say that is alpha is the root, and then you get a new polynomial with complex coefficients. After dividing f of x by x minus alpha, you'll get a new g of x with degree n minus 1. And you will say apply FTA, fundamental theorem of algebra, again to that polynomial, and you should get a beta now, x minus beta out. Similarly, you can extend this process repeatedly n times till you can get n distinct linear factors, right? So the next idea is irreducible polynomials. Irreducible polynomials in C of x. Polynomials in C of x are all linear polynomials. Are all linear polynomials. Why is that so? Because fundamental theorem says that if you have a quadratic polynomial, let's say we have a quadratic polynomial like this. This quadratic polynomial has at least one complex root. So it will be, you can split it like this, x minus alpha, x minus beta and all, right? So any quadratic polynomial in C of x can be, is reducible, right? Because it is guaranteed that it has at least one complex root. Similarly, any higher degree polynomial is also reducible till you get down to the linear polynomials. After you already have a linear polynomial, you don't have any further need to reduce it. You can't reduce it any further. So those are the irreducible polynomials in C of x. So the consequence of that is that any polynomial, any polynomial in C of x can be decomposed, like this. Basically, f of x can be written as an times x minus alpha 1, x minus alpha 2, and let's go till degree n, right? Or you could have a situation where some of the roots are repeated, so you might have multiplicities on each root. So that is also a possibility. So basically, any polynomial in C of x can be decomposed in this fashion. The next idea is the idea of Vieta's relation. Vieta's relations. So for any polynomial equation, we can find sum of the roots alpha 1 plus alpha 2 plus alpha n will be equal to minus of a n minus 1 by a n. And similarly, sum of the roots taken 2 at a time would be a n minus 2 by a n. And finally, the product of the roots taken n at a time would be minus 1 power n a0 by a n. I am sure all of you are familiar with this, so I'll not spend too much time on this. Vieta's relation is a pretty standard result. Let's move on to the next idea. We say that let f of x belonging to R of x. It's a polynomial belonging to a real number set. So basically coefficients have to be real. Be an irreducible polynomial. be an irreducible polynomial. Then fx is a linear polynomial. Fx is a linear polynomial, or fx is a quadratic polynomial, ax square plus bx plus c, with discriminant b square minus 4ac less than 0. So basically, we are saying that in real number sets or in R of x, the polynomials which are irreducible have to be either linear or they can be quadratic with b square minus 4ac less than 0. Remember, we earlier discussed that in complex number sets or polynomials with complex coefficients, any irreducible polynomial must itself be linear, right? Because it always has a factor. So what we are saying here is that for real number polynomials, f of x being irreducible means it must be either linear or it must have degree 2, right? So that is pretty clear. Uh, let f of x and g of x belong to q of x. This is the set of polynomials with rational coefficients. If any root, alpha of g of x is also a root of f of x, is also a root of f of x, and the multiplicity of alpha in g of x does not exceed does not exceed its multiplicity in f of x, then we can say that g of x divides f of x in q of x. So basically, we are saying that if any root of g of x is also a root of f of x, and the multiplicity of the root alpha in g of x is less than the multiplicity of alpha in f of x, then and only then can we say that g of x divides f of x in q of x, right? Similarly, we can also state that let g of x be an irreducible polynomial in q of x if f of x belongs to q of x and f of x and g of x have a common complex root, have a common complex root, then g of x divides f of x in q of x. So g of x is irreducible. So f of x is another polynomial in the same set q of x and they have a common root. Then g of x divides f of x. So we have a common complex root and g of x will divide f of x. Basically, the idea is f of x can be written as x minus alpha times some other stuff. So let's say h of x, and g of x is an irreducible polynomial in q of x. So probably it cannot be further reduced, means g of x itself must be linear but we are looking at the Q of X set. Right? So G of X could be this. Uh, so let's think of a proof for this result, because immediately it doesn't seem obvious how we get this. So let's think about a proof. So because G of X is irreducible, if G of X does not divide f of x, then G of x, f of x basically have GCD equal to 1. They must be co-prime because G of x cannot have any other factor. So if it does not divide f of x, G of x and f of x are co-prime. And we saw earlier in the previous video that if two polynomials are co-prime, so there exist u of x and v of x belonging to q of x such that f of x times u of x plus g of x times v of x must be equal to 1. Since the polynomials are co-prime, their greatest common divisor is 1, and this is like Bézot's lemma, and we are writing f of x times u of x, g of x times v of x must be 1, and there must exist u and v in the q set like this, right? But now the question has already said that f of x and g of x have a common root. Have a common root. So if they have a common root, let's say alpha, now you can say that if you substitute alpha in this, right? Alpha in this, you'll get f of alpha, u of alpha plus g of alpha, v of alpha is equal to 1. But f of alpha is 0 and g of alpha is 0, so you're getting 0 equal to 1. So you're getting a contradiction here. And what was our assumption? G of x does not divide f of x, right? So that assumption must be wrong, and therefore we have proved that g of x must divide f of x, right? So we are getting the proof on the basis of the fact that f and g have a common root and g of x is irreducible. So then if it doesn't divide f of x, they are co-prime to each other, right? On the basis of that, we are able to establish a contradiction. Okay, so let's look at some problems and apply the concepts that we have learned so far, right? So the first question that we look at is this: find the remainder, find the remainder when x power 100 minus 2x power 55 plus 1 is divided by x square minus 1. Pretty simple question. We have to use the division algorithm. We'll say x power 100 minus 2x power 55 plus 1 must be equal to x square minus 1 times q of x. And since x square minus 1 was the divisor, my remainder must be a linear term. Remainder must be a linear polynomial because this has degree 2. So we can say it is ax plus b, right? Now, in order to find ax plus b, I need two equations. I can put x is equal to 1. If you put x is equal to 1, x square minus 1 vanishes and you get basically a plus b is equal to 0. And similarly, if you put x is equal to minus 1, again, x square minus 1 vanishes and you get b minus a is 4, which just tells us that a must be minus 2. Write it here. A is minus 2 and b is 2. So basically, the remainder is r of x is minus 2x plus 2. A pretty obvious application of your standard uh, division of polynomials with another polynomial. Let's look at another question. Prove that prove that the polynomial x power 2n minus x power 2x power 2n minus 1 plus 3x power 2n minus 2 and so on till minus 2nx plus 2n plus 1 equal to 0. Prove that this polynomial has no real roots. This is our polynomial. We have to show that it has no real roots. One way to show that a polynomial has no real roots would be to show that the value of f of x is always positive or always negative or always negative. That would imply that f of x equal to 0 has no real roots, right? So in this case, you will realize that if x is less than 0, if x is less than 0 and even if equal to 0 actually, you will realize that f of x is positive. Why? Because when you take x as negative, all of these odd terms will become negative and negative becomes positive. So overall, the whole polynomial will have a positive value. Now, so that case is anyway done. So we have to look at cases if x is greater than 0. So how do we analyze that? One nice way to do it is to take x times f of x. X times f of x is actually equal to what? It is equal to x power 2n plus 1, 2x power 2n plus 3x power 2n minus 1, and so on till minus 2n x square minus 2n x square and plus 2n plus 1 into x. That is the value of this polynomial, right? Okay, so I'll just do it on the next screen. So what is 1 plus x times f of x? That is basically f of x plus x times f of x. So if you think about that, what was x times f of x? That was x power 2n plus 1 minus 2x power 2n plus 3x power 2n minus 1 minus 4x power 2n minus 2 and so on till 2n plus 1x. And if we add that to x power n, we add that to f of x, which is x power 2n minus 2x power 2n minus 1 plus 3x power 2n minus 2 and so on minus 2n x plus 2n plus 1, right? So what do we get in this case? When you add this, you will realize that this x power 2n and this cancel and become a minus x power 2n. This also minus 2 and plus 3 gets cancelled and becomes a plus x power 2n minus 1. So you will see that you will get this expression x power 2n plus 1 minus x power 2n plus x power 2n minus 1 minus x power 2n minus 2 and so on plus x plus 2n plus 1. Now this is the first few terms here from here till here is a simple GP with common ratio minus 1 by x. So you can use the GP formula and you will get this x power 2n plus 1 by x plus 1 and plus 2n plus 1, which is the last term here, right? And you can easily see that this is greater than 0 if x is greater than 0, right? This is clearly greater than 0 if x is greater than 0. So what we have seen is that 1 plus x times f of x is greater than 0 for x greater than 0, which implies f of x is greater than 0 for x greater than 0. So we have now shown that f of x is greater than 0 in all the cases, not just for x less than 0, but also for x greater than 0. So that concludes our proof. Let's look at the next problem. Here we have, let a be a real number. Determine the number of real roots. Determine the number of real roots of the polynomial x power 4 minus 2a x square minus x plus a square minus a. So I'll show you a technique here that is non-routine. Basically, the idea is a little interesting. Instead of thinking about this as a polynomial in x, we can treat the expression. We can treat the expression as a quadratic in a. Quadratic in a, right? So we can write x power 4 minus 2a x square minus x plus a square minus a as a square minus 2x square plus 1 times a plus x power 4 minus x. I have just rewritten it as a quadratic in a. The benefit of doing that is I can solve this quadratic in a for roots in terms of x, and basically I can factorize it like this: a minus x square plus x and a minus x square minus x minus 1, right? I am able to factorize it because I'm going to use the simple quadratic formula on this, but think of it as a quadratic in a. So basically you will get roots of x square minus x and x square plus x plus 1. Now that I have a factorization, I can rewrite it like this. This can be written as x square minus x minus a multiplied by x square plus x plus 1 minus a, right? So now the entire fourth degree polynomial in x was written as a product of two different quadratic factors in x, right? The trick was to use it as a quadratic in a and use that to figure out the roots of the quadratic a in terms of x. And once you got this factorization, we just multiplied each of the factors with minus 1. Now this is a very straightforward polynomial. It is a product of two quadratics. So depending on the values of a, it can have 4 roots, 2 roots, 0 roots. So you can just check the discriminant of each of the quadratics and decide when a is greater than 3 by 4, it should have 4 roots. When it is less than minus 1 by 4, it should have 0 roots. That is a pretty simple analysis, which I will leave to you, right? You can do that part yourself. Now let's look at another question. This is slightly more complicated. So this is the question. Let m be a positive integer. Be a positive integer. We have to prove that cot square pi by 2m plus 1 plus cot square 2 pi by 2m plus 1 and so on till cot square m pi by 2m plus 1 is equal to m into 2m minus 1 by 3. Okay, so this is what we want to prove. Obviously, here you will have to take advantage of Euler's theorem and De Moivre's theorem. So you will say that we know that cos n theta plus I sin n theta is equal to cos theta plus I sin theta whole power n. And now if you expand this stuff with binomial theorem, you will get cos power n theta plus nc1 cos power n minus 1 theta into I sine theta, and so on, so on. There will be many terms here, n plus 1 terms for this binomial expansion. If you compare the real parts, you will get an equality on cos n theta. If you compare imaginary parts, comparing imaginary parts, you will get an equality on sine of n theta. So we'll take the imaginary parts one. We'll say sine of n theta will come out to be nc1 cos n minus 1 theta sine theta minus nc3 cos n minus 3 theta sine cube theta, and so on. You are getting multiple terms here. You will get all the odd coefficients here, right? Now what we will say is we'll take n as 2m plus 1, and we'll take theta 1 by 1 as pi by 2m plus 1, and then 2 pi by 2m plus 1, 3 pi by 2m plus 1, till m pi by 2m plus 1. So when you take n as 2m plus 1 and theta as this, what you get is simply 2m plus 1 into pi by 2m plus 1. So sine pi, right? 1 by 1, if you write all of these terms, you get basically sine of n pi, n times pi by 2m plus 1, correct? So it is 2m plus 1 into theta, we'll write pi by 2m plus 1. So this time it is becoming sine pi, which is 0. So you're getting 0 is equal to this whole expansion. And the next time you would get sine 2m plus 1 into 2 pi by 2m plus 1, which is still 0, which is sine 2 pi, which is still 0, right? So basically, you are getting this expression is left hand side is 0 in all these situations, and the right hand side is equal to 0, right? So what we can do now, I will just write it here. We'll say 0 is coming as 2m plus 1 c1 cos of n minus 1 theta sine theta minus 2m plus 1 c3 cos of n minus 3 theta sine cube theta, and so on, right? If you divide both sides by sine power n theta, sine power n theta both sides, right? So what do you get now? You get 0 is equal to 2m plus 1 c1. This becomes cot power n minus 1 theta minus 2m plus 1 c3. This becomes cot power n minus 3 theta, and so on, right? Correct. These are the terms that you are getting. But we know that n was 2m plus 1 here, right? If n was 2m plus 1, the identity is 0 is equal to 2m plus 1 c1 cot of 2m theta minus 2m plus 1 c3 cot of 2m minus 2 theta, and so on. And this identity is satisfied for all the different thetas. For theta is equal to pi by 2m plus 1, 2 pi by 2m plus 1, till m pi by 2m plus 1. We had seen that in the previous screen that this was true for all of these different angle thetas, right? So basically, this looks like what? This looks like a m degree polynomial. M degree polynomial with roots being equal to xk, which is cot square k pi by 2m plus 1, where k goes from 1 to m, right? The roots of the polynomial are what? cot square k pi by 2m plus 1. K is 1, it is cot square by pi by 2m plus 1. And the polynomial itself is looking like what? The polynomial looks like this. 2m plus 1 c1 x power m minus 2m plus 1 c3 x power m minus 1 and so on till minus 1 power m 2m plus 1 c2m plus 1 equal to 0. This is my equation, and in this equation if you put x is equal to xk is equal to cot square k pi by 2m plus 1, where k goes from 1 to m. In that case, we will get all the identities that we had already established. We saw that there are multiple results where we are getting equal to 0, right? We are saying that can be replaced by a single equation, and these are the roots. So if you take 1, 2, m for k, you'll get the m different equations that we had earlier, right? So this just basically sets up our problem because we needed the sum of this. So the sum of the roots cot square pi by 2m plus 1 plus cot square 2 pi by 2m plus 1 till cot square m pi by 2m plus 1. The sum of the roots of this equation is clearly 2m plus 1 c3 by 2m plus 1 c1. So basically that is equal to m into 2m minus 1 whole divided by 3. So the whole point of the question was to use De Moivre's theorem to get a situation where we can say that cot squared k pi by 2m plus 1 is the root of a equation, right? We had m terms in the LHS that we needed to prove, so we need a m degree polynomial with those roots, right? And the whole process that we did earlier was to just set up the situation so that we have an m degree polynomial with those roots, right? Okay. Now let's look at the final problem for this video. This question says if theta by pi and cos theta are rational, then prove that cos theta must be one of the following 5 numbers: -1, -half, 0, half, and 1. So interesting question. They are saying theta by pi and cos theta are both rational. Then we have to figure out the values of cos theta and show that it must be any one of these 5 values, right? So let's say that theta by pi is rational, so it is equal to m by n, let's say, where m and n are integers and all. So basically that means that n theta is equal to m pi, right? So from here we can say that cos of m theta is equal to cos of m pi, and cos of m pi is basically -1 power m. Depends on the parity of m. If m is even, it is 1. If m is odd, it is -1, right? So we have this equation, cos of m theta is equal to -1 power m, right? Right. So one way to do that would be, one way to think of cos theta from here is to prove that for any positive integer n, the expression 2 times cos of m theta can be written as an integer coefficient polynomial of degree n with respect to 2 cos theta as a variable. So what I want to do is show that 2 cos n theta can be written in terms of a polynomial of degree n, where my variable of the polynomial, x of the polynomial, is 2 cos theta, right? Because then I will be able to say what are the roots of that polynomial. And if the roots of the polynomial we can figure out, then we'll get values of 2 cos theta from there, right? Okay, so what I'm saying basically here is prove that 2 cos n theta can be written like this. 2 cos theta power n plus a1, 2 cos theta power n minus 1, and so on till a n minus 1, 2 cos theta plus a n. So this is my claim. I am trying to write 2 cos n theta as a polynomial with 2 cos theta as my variable of the polynomial, right? And it's an n degree polynomial. So let's prove this claim by induction. So we can say that for n is equal to 1 and 2, 2 cos theta is equal to 2 cos theta. For this is the n is equal to 1 case. The other case is n is equal to 2. In that case, 2 cos 2 theta can be written as 2 cos theta whole square minus 2. So this is also a polynomial with 2 cos theta as my variable, right? So we have established the base cases. N is equal to 1 and n is equal to 2. I am able to show that I can write 2 cos n theta as a polynomial with 2 cos theta as my variable, right? If we assume that the proposition is true for n and n plus 1. So basically what are we saying? We are saying that 2 cos n theta and 2 cos n plus 1 theta can be expressed as a polynomial of degree n and n plus 1 using 2 cos theta as a variable. We are assuming the truth here for n and n plus 1. I want to prove that it is also true for n plus 2. So for n plus 2, we can say 2 cos n plus 2 times theta is basically equal to 2 cos theta times 2 cos n plus 1 theta minus 2 cos n theta. This is an identity. How do I know this is an identity? Because I can take this minus 2 cos n theta on the other side. Think about it. 2 cos n plus 2 theta plus 2 cos n theta. What is that? So 2 common. This is cos c plus cos t, right? So cos c plus cos t will be 2 cos c plus d by 2. So that will become 2n plus 2 by 2. So n plus 1 theta into cos c minus d by 2. That will be cos theta, which is what I have written here, right? So this is a trigonometric identity. It is easy to prove. And now, because we know that this can be expressed as a polynomial in 2 cos theta as a variable, and this can also be expressed as a polynomial with 2 cos theta as a variable, we are guaranteed that the overall expression here can be expressed as a polynomial with 2 cos theta as a variable, right? So I have proved my proposition. I have proved that basically 2 cos n theta can be written as 2 cos theta power n plus a1 times 2 cos theta power n minus 1 and so on till a(n minus 1), 2 cos theta plus a0, right? Correct. Okay. So now uh, I know from initially from the problem that cos of m theta was equal to minus 1 power m. We knew that initially because theta by pi was equal to m by n, right? So from there, if you put that here, we get 2 into minus 1 power m is equal to x power n plus a1 x power n minus 1 plus a n minus 1 x plus a naught. Here I have taken x as 2 cos theta. I have replaced this as x as 2 cos theta because it is easier to write this equation using x, right? So what we can say now is that the equation looks like this: x power n plus a1 x power n minus 1 to 1 till a n minus 1 x plus a0 minus 2 times minus 1 power m equal to 0, right? This is my equation, and x is equal to 2 cos theta is a rational root of this equation. Rational root of this equation, because the question said that cos theta was rational, right? Now notice that this has integer coefficients. This polynomial has integer coefficients, and coefficient of first term is 1, right? So coefficient of first term is 1. So the rational root now must be an integer, right? The problem has already stated that it has a rational root. So rational root must be integer. Why do we know that it must be integer? Because if the rational root was some m by n, we know that the denominator divides the first term. N divides 1, so that implies n is 1 or minus 1, right? So the overall rational number must be an integer. This is coming from the rational roots theorem. So that means 2 cos theta must be an integer, which is the rational root that we have, right? And if 2 cos theta must be an integer, the number of values it can take is minus 2, minus 1, 0, 1, and 2. These are the possible values of 2 cos theta. So now we have proved that cos theta can take values minus 1, minus half, 0, half, and 1. These are the possible values of cos theta. So that concludes our proof here. A very interesting problem. You should go over the proof once more. And that ends our video on roots of polynomials. We'll look at integer coefficient polynomials in the next class. And we'll look at conditions of irreducibility in that video. So stay tuned for that one, and I'll see you next time.